All right, so this standard, I tried on my iPad. Clearly, the iPad did not work because what it did not allow me to do was take right out of the book and then effectively be able to manipulate that. So I've now set up with screencast-o-matic.com. So hopefully this one works a little bit better. Um, so this standard requires me to. All right, now I'm in Paint file, so a little bit different here. But this standard requires me to say, okay, so we've got an x-axis and a y-axis, okay? Excuse me, in this case, for our textbook, which the textbook does say is arbitrary, this would be our y-axis and z-axis. So we got light, and let's make this look very bright. Let's play with that for a second, okay? And then I'll put this in green. So we got light that is so that is Ki, and then we've got light that is some that's reflected, so that's Kr. And then we've got some that is transmitted through at a different angle because we got an interface right in there, and that's KT. So anyway, so far what we've done is we've said that Z equals 0. That's right there. But what we're doing is that we're moving that axis to some other arbitrary point. And how does that change the math in our equations? So let's go back now to the textbook. There we go. So all we're doing is, so this equation still applies, so that's good. However, what they've done here, and you can see right here, boundary conditions, they've said, okay, our boundary conditions are exactly, let's go back there, Z equals 0. But if that's not the case, we've got to take into account Z. So what does that mean for us? Well, first of all, right here, we've got our Z's. Those go back into there. And then we've got our, and then we have our equation here where we have, or excuse me, in our exponent, we've got Z's in there, and those have to go back in. Those canceled before, but now they're back in play. Now this stuff still applies. The omegas, the frequency of the light, color of light does not change. And I'll explain why here on this other on this page here. So we've got a light wave. So I guess it's orange. It's waving there. And what we're doing here is, so no matter where we place, whether it's here or here, wherever we put the z-axis, it doesn't matter because it's still the same as far as frequency. That doesn't change. What does change is the position of the wave at that given point. So things like frequency or angles, they don't change. What certainly does change is what certainly does change is the electric field at that given point, since the position since the wave is at a different point depending on where we put K. So we know that if we go back to the book here now, let's go back there. There we go. So we go back here. So we know that's true, and we know this is true. We know that is true, and we know that is true. That the index of refraction is the same. We know that that Snell's law is the same, but the spatial components definitely change, and those in there because we have the z components in there. So that may not quite be as true. We've got to adjust it based on the z component now. So okay, so we go on down. So that looks pretty true. Well, no, it's not true anymore because now we have an e to the I component because we've got those z's, and we have to now add in not only because our as you can see up here, our our s's only have an x component, but our y's, but our p's have a y and a z component. So then, so while all we have to do here is add e to the I, we have to add e to the I, and we have to add cosine thetas and sine or y hats and z hats. So as you can see back up here, we're adding in these because all that does is give us our y hats. And because the y hats all cancel each other out, it becomes dimensionless. But we can't assume that anymore for these equations. They're not dimensionless anymore. Interesting. So then, so to get, again, the way we calculate the magnetic field is the same, obviously. Again, that's the same, that's the same, that's different. Same, different. However, what changes again is the value of E that we have to give. So this is all correct right there. Magnetic field in, reflected, and transmitted. However, what they have done here is now they've taken out the z's. We got to add those back in. And what we've done here, and all they've done is again, boundary conditions. Once you throw boundary conditions, it changes everything. Or excuse me, it simplifies it if z is 0. So then, and then this it affects Snell's laws for magnetic field because we've had to change up our or wait, let me restate that. It should not change Snell's law for magnetic fields because Snell's law doesn't change no matter where our z-axis is. I guess I'm not quite sure why it doesn't change Snell's law, but that would be a good thing to explore. But but Snell's laws don't change. So anyway, that is the lowdown of why z equals 0 is so cool. Unfortunately, that a few things, but not everything changes when that's not the case.